Hello friends, today's topic is magnet vibrating in uniform magnetic field. Means in this topic or in this video, we will learn what happens when a magnet, initially the magnet is in external magnetic fields. The red line what indicates? The red line indicates external magnetic field. There, if there is any pole, north pole, south pole, there are magnetic lines of force. So these red uniformly spaced, equally spaced lines indicates uniform magnetic field. So there is external magnetic field. In such external magnetic field, there is a magnet. Magnet is having two poles, no? North pole and south pole, isn't it? So here is shown in the diagram. In this diagram, there is a magnetic field, external magnetic field, and in this external magnetic field there is a magnetic dipole, two poles, north pole, south pole. In this diagram, magnet is not aligned with the external magnetic field. Initially, suppose initially the magnet is aligned with the external magnetic field. So then what will happen? It is still and stationary. So it is, this sentence is here. If a bar magnet is freely suspended in the plane of uniform magnetic field, means there is a uniform magnetic field, and in that external magnetic field a magnet is freely suspended. So then it remains in equilibrium with its axis. Its axis means what? Magnet's axis is parallel to the direction of the field. So red line indicates direction of the magnetic field, and the axis of this magnet will be aligned with this external magnetic field. And so therefore the magnet will remain in equilibrium condition. So if a bar magnet is freely suspended in the plane of uniform magnetic field, it remains in equilibrium. What will happen? The magnet will remain in equilibrium with its axis parallel to the direction of the external magnetic field. Now if it is given a small angular displacement theta, means initially the magnet is like this, okay, and the magnet is slightly displaced, which is drawn here in this diagram. The same diagram is here. The magnet is slightly displaced, so here theta is indicated, which is known as angular displacement of the magnetic axis. See, north pole, the line joining the north and south pole indicates magnetic axis, which is imaginary one, and that axis makes an angular displacement with theta with external magnetic field. Okay, so if the magnet is given a small angular displacement theta, okay, here is explained about an axis passing through its center and perpendicular to itself and the field. So magnet is displaced and released. आता the pen is rolling, the magnet will not happen. If magnet is displaced and it is released, then what will happen? The magnet will start to oscillate or vibrate like this and here. So if the magnet is given small angular displacement and release, it will perform or it performs angular oscillations as shown in this figure. Basically this topic is the topic comes under the S.H.M, simple harmonic motion. The situation here is magnetic field, magnet is suspended in external magnetic field. Then what will happen? The magnet will perform angular oscillations. Okay, this is the basic concept. S.H.M, simple harmonic motion, is the concept in this situation. Now, okay, as a magnet starts to vibrate or oscillate, there will be torque action or torquing action. Here it is explained very well. So let mu, this is a symbol one for magnetic dipole moment. Magnetic dipole moment is symbolized with this letter, Greek letter mu. So now what is meant by this mu means magnetic moment. Here I have explained or written the meaning of magnetic dipole moment. See, the first meaning of magnetic dipole moment, it is the magnetic strength and orientation. Magnetic strength and orientation of a magnet or other object that produces magnetic field. Magnetic moment indicates magnetic strength and orientation of a magnet or other object which produces magnetic field. This is the one of the meaning. Another meaning of magnetic moment is, or magnetic dipole moment, the same. It is a vector quantity associated with the magnetic properties of electric current loops or more generally magnets. It is also vector quantity. Magnetic dipole moment is also vector quantity associated with magnetic properties of electric current loops or more generally magnet. Another meaning of magnetic dipole moment is, it is the measure of objects. Okay, it is the measure of objects' tendency to align with magnetic field. Magnetic moment indicates or gives us the information related to the tendency of any object to get in aligned with the external magnetic field. Here is also the situation. Here is a magnet which is kept in the external magnetic field. We have displaced this magnet slightly, and here the mu, which is known as the magnetic dipole moment, indicates the tendency of that magnet to align or getting aligned with the external magnetic field. So let mu be the magnetic dipole moment. Okay. And capital B, here in physics capital B is the magnetic field, or the magnetic field is indicated or symbolized with the letter capital B in the deflected position. Means magnet is in the deflected position. So in the deflected position, a restoring torque acts on the magnet, which tends to bring it back to its equilibrium position. Means initially our magnet is in equilibrium condition. We have displaced it in slightly, giving it angular displacement theta. As soon as we release, that torque tends to or brings to back to its original position. That tendency is, or that restoring torque brings the magnet to its equilibrium position. So in deflected position, restoring torque acts on the magnet that tends to bring it back to its equilibrium position. Here we used a symbol mu for magnetic dipole moment, as symbol M is used for the mass. So many times M is also used for the magnetic dipole moment, but here in this topic this mu letter is used, which is clarified by the publisher. Now another physical quantity, torque. So the magnitude of this torque, here we have mentioned the torque acts. Okay, so the magnitude is given by this formula, mu into B sine of theta, where theta is the angular displacement, mu magnetic dipole moment, and capital B is the magnetic field. So torque tau, this is also Greek letter, torque tau equal to mu B sine of theta. If theta is very very small, then sine of theta can be taken as theta radian. So instead of sine theta, we can write theta radian. So torque tau is equal to mu B sine of theta. Now here condition is given for clockwise angular displacement. If the displacement is in clockwise direction, means in the direction of clock. So for the clockwise angular displacement theta, the restoring torque is in anti-clockwise direction. Please notice this thing. If clockwise angular displacement, then torque will be in the anti-clockwise direction. So here torque is equal to I into alpha minus mu b theta. Now what is meant by capital I and alpha? Here it is given, where capital I is the moment of inertia of a bar magnet. We know that this term moment of inertia. Okay. So where I is the moment of inertia of a bar magnet and alpha is angular acceleration. So with the help of this formula, we can write angular acceleration alpha is equal to minus mu b upon capital I into theta. This bracketed quantity mu is constant, which is magnetic dipole moment. B magnetic field, which is also constant, which is not varying quantity. I capital, which is the moment of inertia, that is also constant quantity. So this bracketed quantity is constant. So mu b and I are constant in this equation. That indicates or that shows that angular acceleration is directly proportional to angular displacement. Means as angular displacement increases, angular acceleration will also increase. If angular displacement is decreased, angular acceleration will also decrease. There is a direct proportionality which is mentioned here. Angular acceleration is directly proportional to angular displacement and directed opposite to the angular displacement. This negative sign indicates angular acceleration and angular displacement are oppositely directed. Means if angular displacement is in clockwise direction, angular acceleration will be in anti-clockwise direction, vice versa. Hence, the magnet performs angular S.H.M. S.H.M means simple harmonic motion. Like this, magnet will perform simple harmonic motion when it is kept in external magnetic field. That is the concept of this topic. Now when the magnet is performing simple harmonic motion, then there should be a physical quantity period which should be taken in account. So period of vibrations is given by this formula. Now period of vibrations of what? Of magnet is given by this formula, capital T, which is equal to 2 pi divided by under root angular acceleration per unit angular displacement. Angular acceleration per unit angular displacement. So period of vibrations of the magnet equal to 2 pi divided by under root alpha upon theta. Ultimately period equal to 2 pi under root I upon mu b from this formula. So this is about magnet vibrating in uniform magnetic field. Hope you will like this video. Thank you so much. Please comment in the box.